Oh, good evening, everyone. We are starting our evening lecture program, and today we'll have, right now we'll have one of our top speakers, who is Kyunghyun Cho. And let's try to connect with him. Hello. Can you hear us?
Yes.
Yes.
Okay.
Cool. So guys, now we'll have a talk by Kyunghyun Cho, who is an assistant professor in the University of New York. He has his own group, which is working on machine learning and NLP problems. So let's greet the speaker.
I guess you should share the screen here.
Yes, you can share your screen. Yeah.
Okay, let's see. Can you see my slides there?
Yes.
All right.
Well,
Thanks for the invitation. I hope you are enjoying the hackathon now. So I saw the leaderboard, and then people are actually making a lot of progress. I can see. Yes, that's really nice. So today I was going to talk about some of the recent advances in neural machine translation, starting from the very beginning, and then if time permits, I'll try to talk about some of the latest research that I've been doing. So I'm currently at New York University and doing some part-time research scientist work at Facebook AI Research as well. So one of the most, the interesting thing about the recent advances in natural language processing is that we have somehow moved on from the discrete sequence of symbol, which is the usual, let's say, text, how we understand the usual text, into the continuous representation. So what it means is that we are going to project that discrete sequence of sequence of discrete symbols into the continuous space, and then we do some kind of manipulation within that space. Now, why do we want to do that? It turned out it can actually allow us to do a lot of interesting things. First one is, we can share across multiple modalities. So you can think of having a text in one language, text in another language. You can think of having an image, video, whatever the data you have. And then now, as long as you can project it into a continuous vector space, now we can constrain those mapping so that all those different modalities are going to be mapped to the single shared space. And then we can now manipulate the data regardless of how they were presented initially, right? So either in text, like images, video, or whatnot. And then we can do the manipulation while sharing the information across multiple modalities. Second thing is that it turned out we can actually do a lot of interesting things within the continuous vector space, because continuous vector space gives us a possibility of using many of the existing optimization algorithms. It's much easier in the continuous space than in the discrete space, where the problem becomes combinatorial optimization. So the neural machine translation started to become, let's say, widely adapted since 2014. And then the idea is really simple. We have an input that is a sequence of discrete symbols, and then that input is going to be projected into a continuous vector space using an encoder that is often a recurrent neural net, but nowadays you can use convolutional neural net or even the transformer, which uses the attention only. And then once we have that continuous vector sequence, we're going to have the decoder, often augmented with the attention mechanism, to decode the sequence of continuous vectors into the sequence of target symbols. And then now suddenly it becomes the translation system that can be trained end-to-end. And also, interestingly, this translation process, which happens within the continuous vector space, the space is completely stripped of the actual linguistic symbols. In other words, the decoder, together with the attention mechanism, does not really see the surface form of the input. So it doesn't really know whether the source sentence is written in Korean. It'll just look at the continuous vectors extracted by the encoder. So there are some interesting implications that we are going to exploit in order to build a much more interesting neural translation system. And then it seems like everyone is using neural machine translation these days in the machine translation, both in industry and academia. So I decided that, okay, so when did it all start, right? And then I looked for it like really, like carefully, and then the first, let's say, mention of neural machine translation was from the CFAR Deep Learning Summer School in 2014. And then that's been only 3.5 years now, right? And then somehow nowadays it's become completely standard. So Google decided to use the neural machine translation in their production. And then Microsoft quickly followed up and then started deploying their neural machine translation system in their production. Facebook, of course, couldn't wait. And then Amazon recently released their API to be used in their cloud service. And then that API for the translation service is also implemented using neural machine translation system. Systran, which is one of the oldest and largest machine translation service company in the world, also started using neural machine translation. Even the European Patent Office started to provide the translation service of the patents using the neural machine translation. And Booking.com, I guess nobody uses Booking.com anymore. Everyone uses Airbnb. But Booking.com also uses the neural machine translation to translate not only the description but also the reviews. And it turned out that the customers actually don't even realize often that the description was translated automatically. So that's really interesting. But now, let's try to see what we can do even further instead of building a single pair language translation system. So what we can do is, because the decoder does not really care about what the source sentence was, and then also the encoder only transform the source symbols into the continuous vectors regardless of whatever the other purpose or the downstream task those continuous vectors are going to be used for, you can now think about building a multi-target translation system. Now we're going to use one encoder that's going to encode or project a source sentence into the continuous vector space. In the slide, what you're seeing is the Korean sentence, and then encoder is going to simply turn it into a sequence of continuous vectors. And then once that has been done, the decoders do not really care in which language it was written in. It only looks at the continuous vector space, meaning that we can have multiple decoders for each of the target language, and then the decoder is going to look only at the continuous vector space and then learn to decode whatever the language it is responsible for. And then it turned out to work pretty well. It was presented in ACL 2015 by the folks from Baidu. And then what they showed is that you get an improvement in some of the languages because the shared encoder now knows or gets more information about the language via multiple corpora. And then now, we saw that work, and then we were thinking, okay, so that's good, but can we be more ambitious? Perhaps what we need is to have the multiple encoders as well. So as long as each of the encoder can project whatever the language is responsible into the shared continuous vector space, then from there on, the decoder can decode out into whatever the target language it is responsible in. So what we did together with Orhan Firat, who is now at Google Translate, is to build a multi-way, multilingual translation system that's going to have as many encoders as there are source languages, and then as many decoders as there are target languages. But we're going to share the attention mechanism so that we're going to have one system, one part of the network that is used for every single pair you can think of in this system. And then this actually worked out pretty well. And then we thought, okay, this is amazing because it's essentially the first convincing evidence that we can build a multi-way, multilingual machine translation system using the neural net. That's what we thought. That was a good idea, except that was not true. The very first such system was proposed in 1992 by Lonnie Chrisman, who was back then at CMU. And then already back then, some of the visionaries back then already thought about this kind of system. They knew that the continuous representation allows us to share information across different modalities, different languages. And then what Chrisman proposed was to use the autoencoder together with the translation system, so that he tried with the two encoders, one encoder for English, the other encoder for Spanish, and then also two decoders, one decoder for English, one decoder for Spanish. And then he was able to show that he could actually train this model to translate from English to Spanish as well as Spanish to English simultaneously. So it's essentially the revival of all the old ideas, but with the better, let's say, better learning algorithm, better model architecture, and of course, better computational resource. And then what we noticed was that we can actually share this attention mechanism, and this attention mechanism is completely different from what we thought the alignment does. So if you go all the way back into the, again, early 90s and late 80s, IBM folks back then proposed a word translation model that specifically extracts the alignment of the words written in two different languages. And then if you think about it in that way, it doesn't make any sense to share the alignment mechanism across multiple language pairs. Of course it doesn't make any sense. But because, again, we work in the continuous vector space with the very many dimensions, what this alignment or the attention mechanism can do is to find the alignment at the semantics level or some kind of underlying regularities level. So what you're seeing on the screen is the alignment between the four language pairs, four directions, and then these alignments were extracted by a single attention mechanism. And then still you see that this is showing much very reasonable thing. And then we have a few more examples in our paper together, written together with Johan. And then one alignment mechanism can be used for, let's say, 8 or the 16 different directions, and then still we see that it gives us a very reasonable alignment. So then, of course, everyone started thinking that okay, so the multi-way multilingual translation system works. Then why don't we make it into a multimodal translation system? So the idea is that we can always project various different modalities into the continuous vector space. All we need to do is make sure that they are all compatible. So Desmond Elliott et al. Decided that okay, we gotta do something with the images as well. When professional translators translate a text, they do not only look at a sentence, but they look at a lot of other things. When they are doing the interpretation, they do look at what the person looks like or how the person expresses when the person speaks in order to translate better. And then when they translate a book, they're going to look at all those, let's say, external knowledge in order to translate better. So one of the early attempts, or the recent attempts, which started last year, is to have a multimodal machine translation system for the image captions. So now the goal is to translate a caption, but can you translate a caption if you know which image the caption was describing? Well, so far, it has not shown us much of the improvement. A lot of people are working on it. We do get some marginal improvements, but I believe this is a really nice way forward. And then at the end of the day, what happens is, to the neural nets, these, let's say, words in Korean, words in, let's say, Russian, words in French, they don't really mean anything. What neural nets see is just a sequence of one-up vectors. And what it means is that we don't really have to bother having separate encoders for separate languages. We can just have one encoder that's going to look at whatever the sequence of one-up vector is, right? It's all about just how we encode the things. And then just let it project whatever the sequence into the continuous vector space, and the decoder is going to just take care of it, right? Because decoder, in fact, never sees that how the source sentence was written in. So my group actually tried it out with the characters. So we used the Latin characters and Cyrillic characters to represent the sentences written in any of the European languages and also some of the, let's say, I don't know, languages that use the Cyrillics, I don't know how you call it in general. And then we were able to train a system to have a single encoder that's going to read a sentence written in Czech, German, Russian, and Finnish, and then trying to translate it to English. And then it turned out you can just do that without even knowing which language the source sentence was written in. And then, based on that, the Google Translate went even one step further, realizing that hey, we can have just a single decoder as well. Again, what decoder is in fact outputting is a sequence of one-up vectors. And the neural net doesn't really know, like what Cyrillic letters are, what Korean letters are, what Chinese letters are. It doesn't really matter. It's going to just generate a sequence of one-up vectors based on however we built the vocabulary for. And then it turned out that that's possible by just giving a single language identifier at the beginning of the source sentence. And then all you now need is the encoder and decoder, single each one of them, just one of them, regardless of how many source languages or how many target languages you have. And then the nice thing we get out of this is that it really helps with the low resource language pairs. because all the knowledge extracted from the high resource language pairs are going to be useful for the low resource language pairs, and then somehow they work as a very good regularization method. So let's just look at one quick, let's say, character level encoder and the decoder that we have worked on. So character level, one of the issues with like using all those, let's say, fancy encoding or the very dumb encoding is that when you go for a lower and lower level, the length of the sequence grows tremendously. So you have to be a bit careful and like, let's say, smart about how to build the encoder in order to both capture all the regularities underlying the source sentence as well as to reduce the computation. So what we did in our TACO paper this year was to first start with a multi-width convolution for character level sequence that was proposed by the Yoon Kim et al., who is now at Harvard but who was at NYU back then in 2015. So you can think of this kind of convolution as a n-gram matching machine. So it's going to detect what kinds of n-grams are there, and then by using the multi-width convolution, we are essentially capturing character n-grams that's going from the unigram, bigram, trigram, and so on until the 8 grams. And then once we have applied the multi-width convolution, which is embarrassingly parallel, what we can do is we can now reduce the length of the sequence by using the max pooling. And then this max pooling is fine, it's not really losing information because we have applied a multi-width convolution earlier step. So it's going to just, like trying to figure out some of the locally translation invariant features or the n-gram features in the source sentence. And we have to feed it through the highway network or ResNet in order to learn those nonlinear mapping between the spelling and the meaning. Once then, you can just use the usual bidirectional recurrent neural net or your choice of between, let's say, CompNet or the attention is all you need on top of that. And then what it turned out is that we can train a multilingual system that goes from German, Czech, Finnish, or Russian to English without even giving the language ID to the source encoder. So encoder is going to just look at the sequence of one-hot vectors where each of the one-hot vector corresponds to one of the characters. And then the encoder is going to simply figure out in which language it was written in and then trying to translate it into the English. And what you see in the slide is that doing this kind of multilingual translation generally helps without increasing the number of parameters. So we train the model with the same number of parameters using all these 4 language pairs, and then compare it with the 4 different, let's say, single pair models, and then each of the single pair model has the same number of parameters as this multilingual model. And then what we see is that in terms of the blue score that you are all using now as the evaluation metric, this multilingual system helps, or sometimes similar. But when you look at the human evaluation, the fluency is one of the human evaluation metrics that we use. This multilingual system is much more fluent. And the interesting side effect is that it's very, very robust to the intra-sentence code switching. So on the screen, you see an example of a source sentence we created ourselves that starts with the German, and then in the middle, it switches to Czech, and then it comes back to German, and then at some point it switches to Russian, and then like finish by going back to German. And then obviously this kind of sentence does not exist in the training set. But our model, which was trained without knowing which language, source language, the sentence was written in, can just cope with this without any problem, because it just looks at it as a sequence of one-hot vectors, and the model has learned how to find the regularities that are shared across different languages. So once the encoder has projected this kind of weird sentence with the intra-sentence code switching, the decoder just decodes out the English sentence, and then it's pretty perfect. And then this is getting more and more important because of the social media where, let's say, bilingual speakers, like mix in different, let's say, languages in one sentence. And I believe the hackathon's, let's say, goal is to do the IT, let's say, sentence translation, right? Document translation. And there, what you see is that when you try to have the technical terms, sometimes those technical terms do not really have the corresponding words in the target language, and then you need to be able to cope with, let's say, multiple languages. So it's a really interesting directions, and then people have started pushing forward, And then in the case of Google, Google Translate released a blog post last year showing that they are actually using this kind of multilingual system in production. Okay, let's see. So, like we thought, okay, this is really interesting. What is the next thing that we can do? And then we started thinking about what the humans actually do, and then how it differs from the current state of the neural machine translation system. So neural machine translation today, or any kind of supervised learning based deep learning these days, can be thought of in two stages. First, we do the compression, and then after the compression is done, we do the pattern matching. Why is that? Because we're going to train a network using the gigantic training data offline, and then once the training is done, we throw away the training data and then deploy only the neural network. What it means is that the neural net needs to have all the important regularities extracted from the training set stored or compressed into its finite number of parameters, and then given that, when the new example comes in, it does the very quick pattern matching and then answers. Now, what's the issue with this? The issue is that it becomes increasingly more difficult as the data set size grows, because the neural net must grow accordingly. Unless we have the perfect compressor, what we need to do is, in order to store more regularities, we just need to have a larger neural net. And then eventually it becomes a bit of a problem. So what we realize is that that's precisely not what human translators do. What human translators, or any kind of person, or you or me in this room, what we never memorize everything. It's impossible. What do we do then? We have books. Long time ago, people used to go to library, but these days, I guess everyone uses Google, or in Russia, is it Yandex? I guess, you use Yandex, right? So even me, so I'm supposed to be an expert in recurrent neural net, but if any of you or anybody asks me a question about the recurrent neural net, what I'm going to do is I'm going to go into the Google, search for recurrent neural net, even search for my own paper, and then trying to make the answer that's as accurate as possible. Now, what that says is that what we need to learn, or what we need to train a neural net to do, is not to memorize everything or every pattern from the training set, but to learn how to use the vast amount of information. And then what we decided to do was, okay, let's try to incorporate some of the components from the information retrieval into the neural machine translation system, so that the neural machine translation system is going to be trained to use the training set even during the test time without having to memorize everything. So we decided to introduce something called search engine guided non-parametric neural machine translation system. Now here is slightly different from the existing one, where the neural machine translation system only took as input a single source sentence. It's going to take as input a source sentence together with a set of retrieved training examples, and then that retrieval was done using an information retrieval system, such as you can think of just the usual search engine, over the training set. So we're going to have an information retrieval system that indexes the entire training examples, and then when there's a new test example, or the source sentence, the source sentence is going to be used to query relevant training examples. And then now our non-parametric neural machine translation system is going to take as the input source sentence as well as the retrieved training examples, which contains both the source and its corresponding translation. And now decoder is going to have an option to either generate the word or the symbol on its own, or to copy over from the retrieved examples. And then this model is much more scalable because the network has absolutely no reason to memorize the entire thing. Whenever there is something similar, it can just assume that, okay, something similar will be retrieved, so I can just copy over. So it's a very interesting concept, and then we tested it on a simple, let's say, corpus related to a law, and then, like there are a lot of things overlap, so we tried to see, if the neural machine translation system with the memory component and the retrieval can cope with that really well. And what we saw is that, yes, indeed, when the retrieved examples are similar, the neural net can learn to copy over as much as it can in order to get the highest BLEU score you can get. So that's going to be presented next week at AAAI. And then it's a really nice paper. I highly suggest you to read it, yes. And then especially in the case of the technical document or in a domain where the writing style is very well established, it's going to be especially useful. Now, and then we thought, okay, this continuous representation is pretty cool because it's just a continuous space, meaning that we can compute a lot of interesting quantities without having to go through all those combinatorial optimization procedure. We can compute the mean easily, we can compute the variance easily, we can compute all those, let's say, higher order statistics. Now, then, can we use the continuous representation space, continuous vector space, to align two distributions arising from two different languages, and then learn to decode from that aligned distribution without having any kind of correspondence? And that becomes the idea of the unsupervised neural machine translation. So I still left the references, those two papers, as the archive papers, but they have both been now accepted at iClear and will be presented in April, I think, in Vancouver. So both of these papers decided to investigate the idea of unsupervised neural machine translation. So we're going to have two encoders or one encoder. We have already learned that it doesn't really matter. It's going to have either two decoders or the one decoder. As we learned, like that doesn't really matter. But we're going to train them to translate between two languages without having any sentence-aligned corpus. So before going into the detail, we need to think about the cross-lingual word vectors first. So in recent years, let's say starting from the last, 2 years ago and the last year, what we learned is that we can actually get a very nice cross-lingual word vectors. When I mean cross-lingual word vectors, that is that the vector you're going to get for each of the word in any of two languages is going to be close to the vectors you'd get for the similar words in the other language. So if I get the vector for the, let's say, word cat in English, it's going to be very close to a vector you'd get. I think the chat is the French word for cat. Yeah, chat, right? So then you can essentially build a dictionary. In 2015 or so, we were doing that using actual dictionaries. So we get the word vector separately, we have the dictionary, we are going to align that so that the dictionary entries will correspond to each other in the continuous vector space. It turned out, around last year and the year before, we realized that we don't really need to do that. The whole field realized almost simultaneously that we don't need to do that. We can just match the distribution without having the anchor points, and still we get a very, very nice dictionary mapping. And then in the worst case, what you can use is just the numerals. So you can use 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1999, 1998, and so on, because those are pretty universal across multiple languages. So there were a number of papers showing that that's possible, and then now we're going to build upon this and then trying to get the unsupervised neural machine translation system. So I'm going to focus on the paper I have co-authored together with my collaborators in the University of Basque Country in Spain. And then there, what we do is we start with the denoising autoencoder. So we're going to share one encoder across two languages, L1 and L2, and then we're going to have decoder for each of the languages. So L1 decoder and L2 decoder. And then how we are going to represent the source sentence is to view it as a sequence of the cross-lingual word vectors. And then now that sentence, regardless of which language it was written in, is going to go into the shared encoder. That encoder is going to project it into the continuous vector space, regardless of which language it was written in. And then, depending on which language it was written in, we're going to use one of the decoder to reconstruct the source sentence. And then we add some noise in the input in order to the denoising autoencoding. So this is good in a sense that the shared encoder now learns to map two languages into a common shared space so that it can be decoded out by the two different decoders. So this is good, except that it's not enough. The reason is that the decoder knows how to just decode out the words, and the encoder knows how to put all the words into this space so that it can be decoded out later, but it doesn't know much about the language structure itself. So what we did was to use the idea of the back translation to train the decoder further to know about the actual language structure. So what we are going to do is we're going to go from a excuse me, sentence written in language 1 and then we're going to decode it using L2 decoder. Now it's a pretty horrible translation, but then we will use that as the source sentence, and then trying to ask the encoder and decoder to translate into the original source sentence in the L1. Now what it does is that now it forces the L1 decoder to learn about the sentence structure itself, what the syntax is. So this procedure is teaching the decoders to learn how to properly put the words that have been encoded by the encoder into the right place. So you get the actual sentence. And then it turned out it's much better. And then these are some of the results. We have some updated results, but what you see here is that if you do the word-by-word translation, that is essentially the dictionary mapping. So you're going to take one word, you look up into the dictionary, again using the cross-lingual word vector, you're going to find the nearest one in the target language, you're going to just swap it. In French and English, it actually works pretty okay. So you get the blue score of 10 if you go from French to English. If you go from English to French, you get the blue score of 6. It's still very, very horrible, as you can see. And then if you just do the denoising autoencoding, that's the first stage, then what you will see is that it's doing worse than the word-by-word translation. But by incorporating the back translation, in order to teach the decoder what the syntax of the target language should be, we see that the performance goes way above the word-by-word translation. And then I have to emphasize once more is that this is not really using any of the aligned sentences. The network or the learning algorithm does not know how the sentences align with each other, and then still this model was able to learn how to translate. And then similar result was reported also by the Facebook AI research people in Paris, Guillaume Lempo and others. And then that paper uses the generative adversarial learning, or the adversarial learning, to match the distributions between the source and target languages in order to do the unsupervised neural machine translation. So that paper is also really nice. I highly recommend you to read it. So we'll go to the next topic, but before that, do you have any questions?
Does anyone have any questions, guys?
No, not really. My presentation is often really clear, so nobody really has questions.
We'll save questions to the end.
Yep. Okay. Okay, that's good. So at the beginning, I talked about learning to decode. What did I even mean by learning to decode? So first thing to notice is that the decoding anything or the finding a source sentence from a recurrent neural net language model is really difficult. Finding a good sentence. First of all, the state space, that is the space of the sentence, is gigantic. It grows exponentially with respect to the length of the sentence, and then even the even the consonants is really large. So let's say your vocabulary consists of 1 million tokens, and then let's say your sentence is on average 20 to 30 words long. That's already 1 million to the power of 20 or 30. And then it's impossible to exhaustively enumerate all the sentences in that space. And the unfortunate thing is that there is no obvious way to reduce this search space with a recurrent neural net, because it's non-Markovian model, so we cannot really do the efficient dynamic programming. It's not linear, so we cannot really do the forward-backward algorithm, use the, let's say, common filtering type of algorithm. So we usually just rely on the chip and the proximal search, and like greedy decoding is going to be the computationally cheapest, but most approximate algorithm. We use the beam search. It's quite expensive, but it's known to be better than greedy decoding. There are a few other algorithms in between, but the unfortunate thing is that we don't even know how good these approximations are, because we don't know what the upper bound should be. Nobody can actually enumerate it. We can enumerate it in a very, very small setting, but that doesn't really tell us too much when the state space grows exponentially. And then there's another question. This is probably more important, is that our decoding or the inference so far has been to find a sentence that's going to maximize the low conditional probability learned by the model. But there's a question of whether that's what we want. Maybe what we want is not to find the solution that has the highest probability according to the data. Maybe what we want is, we want to have some other decoding objectives during the production time or during the test time. So if you want to make a machine translation system for real-time conversation, quality matters, but the delay is as important. So the Microsoft Skype translator initially was deployed with the disastrous result because it took like 10 seconds for each utterance to be translated, and nobody was going to wait for 10 seconds to have whatever the other person said to be translated. It doesn't make any sense. And the machine translation if I wanted to build a machine translation for the students in high school or middle school or primary school, I probably want to have the high quality, but at the same time want to have the difficulty of the translation to be low. If you want to do the on-device translation, I want to consider not only the quality, but also the computational complexity. And then unfortunate thing is that even if we knew the decoding objective, there is almost no data that we can use to explicitly maximize the decoding objective. In the case of simultaneous interpretation, there's almost no data with timestamp. There are few data, but often they are really small. And then, like parallel corporal with the controlled levels of difficulty, you can consider it as just non-existent. There are a few you can find from the literatures, but it's really difficult to use it to train a full, let's say, neural machine translation system. So why does the decoding matters? Let's take an example of the neural abstractive summarization algorithm model. So it's a really fascinating problem. So it's the extension of the machine translation system where the source is going to be a long paragraph or article, so such as the news articles shown here, and then the goal is to build a succinct summary of the source article. So it's it's just translation, except that the source is going to be an original article, target is going to be a summary. And then, people have been working on it using the technologies from the neural machine translation. And last year, Abigail C. and Chris Manning from the Stanford wrote a paper and then proposed a network called the pointer generator network. So it's a really nice idea. The idea is that we're going to have a source sentence, and then we're going to have the usual attention-based encoder and decoder. But when we compute the actual distribution at each time step, what we do is we're going to either generate from the original distribution or to generate from the copy distribution defined by the attention weights. So decoder has an option to either emphasize much more what the words in the source article, or to generate from whatever it believes should be the output. So it's a very simple idea that turned out to work really well, especially for summarization. And then they called it neural abstractive summarization algorithm. So these are the details, but because of the timing, I'll have to skip. And then what they showed was that this pointer generator network does amazingly well because it has the copy mechanism. So ability to copy over the tokens from the original article compared to the vanilla attention-based sequence-to-sequence model. So that was all good. But now they had a section saying that how abstractive is our model. So far in production, the best summarization system is extractive. The idea is that you have an article, you're going to find some of the sentences or phrases that best summarize the entire article, find them, and then put them together. And then the goal, or the whole promise of the neural abstractive summarization was that it's not going to do the extractive summarization, but it's going to actually make the new summary that's going to succinctly describe the whole article. Unfortunately, it turned out that it's not doing that. The pointer generator network, which is supposed to be a neural abstractive summarization system, if you look at the overlap between the summary and the original article, then pointer generator network summaries, if you look at the bigram, 5 gram, 10 gram, even up to 25 grams, about 20% of the 25 grams in the summary are exact copy, verbatim copies from the original paragraph. Meaning that it's essentially just copying over the entire thing. Just looks at the small subset, copy over the entire thing. So is it because of how the data set was built? It turned out that that's not the case. So we looked at the actual reference summaries. Overlap is almost non-existent. There are some overlaps in the bigram and up to 5 grams, but from there on, there's no overlap. So what this is telling us is that there is some gap, and then what neural abstractive summarization algorithm is not doing abstractive summarization. So what we decided to look at is that, okay, can we actually avoid this issue by only looking at the decoding or the inference algorithm? So what we decided to do was to ensure that the discrepancy between the mixture coefficient or the copy proportion during the training and copy proportion during the decoding by manipulating the beam search procedure of it. So we decided to put an extra term in the beam search scoring function that's going to essentially minimize the difference between our target copy proportion and the copy proportion so far has been used. So it's a very simple idea, but that actually allows us to control the amount of, let's say, abstractiveness or the extractiveness. What this is telling us is that this decoding actually does have a lot of influence on how our network does or how our machine translation system works. And then we can control the behavior by changing the decoding algorithm. And then we see that we can get much more abstractive summarization. This paper is now under review. Hopefully it's going to get in, but I'll be able to update you later, hopefully soon. So what it means is that we can change the behavior quite severely or just significantly by changing the decoding algorithm. But the issue is that making a new decoding algorithm is extremely difficult. It's almost impossible to come up with a decoding algorithm for any arbitrary decoding objective. Each and every one of them is going to be a full paper on its own. Now, then what can we do if we cannot really do so? Let's say we know some decoding objective function, or we know how to evaluate the decoding objective function, but we cannot build the decoding algorithm ourselves. Then what we can do is, because we are machine learning people, we're going to learn a new decoding algorithm. So before going into that, we need to think about just one thing, is that the neural net is nothing but a forgetting machine. It's all about how to forget the information. Let's think about building a deep convolutional neural net that is going to detect whether there is a panda or not. Now we start with the panda picture, and the first few layers of the convolutional neural net needs to separate out foreground from the background, and then throw away or forget about the background. And then it needs to now detect different objects, and then throw away all the objects that are not panda-like. And then within the panda, now it needs to detect the face and the torso, and then throw away the torso. And then only then the network can say whether it's panda or not. Now what it means is that you go from a gigantic amount of information, and then all the way to just a single bit information. And on the way, what it needs to learn is to disentangle features, and then throw away or forget about those irrelevant features. Equivalently, you can say that the hidden layers in a neural net contain much richer information than the information in the output. And then it contains the information that goes beyond the task that you trained your neural net for. So now we're going to try to exploit this fact. But the first question we need to ask is, what kind of information are there? So in the case of computer vision, let's say deep convolutional neural net for the images, we actually have a pretty good idea these days. Already from 2014, when the Matt Ziller and Rob Fergers, who were back then, both of them, when Matt was a PhD student at NYU with the Rob Fergers, they were able to show very nicely that the earlier layers of the deep convolutional neural nets capture the edges and corners, and then later layers capture the textures, object parts, ultimately the entire objects on its own. And it was confirmed furthermore by the Yosinski error, so the Jason was able to show that it is indeed true using the techniques called, let's say, deep visualization. And then in the case of language, we haven't had much of the success. So Andrei Karpathy had a nice tech report on arXiv showing that the LSTM is able to capture the brackets, and then talk about the agreement and so on. But it was really, really limited. And then I wouldn't even, it was really difficult to quantify it. And then there was a very, a big fuss about the sentiment neuron found by the OpenAI team last year. So they trained a character level recurrent neural net on a large corpus, and then they found that, there's one neuron that turns on when the sentiment is positive, and when it turns off when the sentiment changes to negative. So everyone was excited, but I was also excited, but at the same time I was pretty desperate, because wait, is that the best we can do? So it just means that we have absolutely no idea what all the other neurons are doing. So we are actually almost, let's say, completely oblivious to what's going on inside the recurrent neural net. And then I did, look at some of the activations, and then indeed you cannot really tell what's going on there at all. So we decided to come up with a new framework called Trainable Decoding by looking at the recurrent neural net language model as a reinforcement learning environment. So the recurrent neural net language model is going to define an environment, and it is environment, right? So there is a temporal dynamics. And then, depending on how we give the input, the dynamics change. And then the change of the dynamics we can actually observe by looking at the hidden state of the recurrent neural net as well as the output. Now it's actually just an environment. And then on top of that, we can now train an agent that's going to observe the state of the recurrent neural net and then tries to inject the signal back either as an input or as the direct injection to the hidden vector to change or manipulate the behavior of the environment. And how is it going to be trained? We're going to train it to maximize the reward at the end. So it's a traditional reinforcement learning scenario. And then it turned out that is precisely what we do with the decoding. Somehow we've been using a fixed agent so far that was manually designed, but that's not a good idea. So what we're going to do is we're going to use policy gradient to train a decoding algorithm in this RL environment. So it turned out it's actually pretty doable. And then I'm going to just go into one example that is simultaneous translation that was done together with the Jiatao Gu, who is joining Facebook AR research soon from this summer, and Graham Newbeck, who's at CMU, and then Victor, who is a professor at Hong Kong University. So simultaneous interpretation of the translation is a fascinating problem motivated by the simultaneous interpretation which started at the Nuremberg trial after the Second World War. The idea is that you want to minimize the delay between the source sentence being spoken and then translation being completed. And source word is going to arrive one at a time. And then, so in order to minimize the delay, translation has to start even before the complete sentence arrives. And then the goal is to maximize the quality while minimizing the delay. And then delay is going to measure between the time when the source sentence is completed and then the translation completes. Unfortunately, we don't have data to train such a simultaneous translation system. We cannot really train it on the RL setting in the production because most of the translation initially are going to be garbage. Nobody's going to allow us to test it in the simultaneous interpretation environment. So what we do is we start with the usual machine translation system. We train using all the corpus we can think of, just a consecutive translation corpus. So one source sentence for, let's say, translation. Once we train a model, we're going to fix it. We are not going to touch the parameters of that model, but we're going to introduce an agent that looks at the hidden vector. So the hidden state that consists of the decoder's hidden state, previously decoded word, and also the context vector from the source sentence after the attention. And then based on that, this recurrent agent is going to decide whether to wait for the next source word or start generating the translation. And then this is just a binary decision. And then we train this agent together with this neural machine translation system. Of course, we don't touch the parameters, but we have to run it, right? Because this is the environment. Using the policy gradient to maximize the reward that's going to be defined as a trade-off between the quality and the delay. And then what we learned is that we can actually train it really easily. And then we didn't need any kind of data for the actual simultaneous translation. And then we can minimize the delay. And then delay can be defined as the shaded area in this kind of figures. Now, what happened is that, okay, so we have the consecutive translation. This is the best you can get. This is the word-by-word translation, that is the blue star. And then what we see is that if we design a simultaneous translation ourselves, without looking at the hidden vector, because we don't know how to interpret it, we cannot really get any better than word-by-word translation. Because we're going to lose the delay if we want to increase the quality. So those are those points that are under the blue shaded eclipse. Is the algorithm designed by myself. So I designed the algorithm manually myself, and then it doesn't really do well. But if we train a decoding algorithm directly to be aware of the underlying neural machine translation system, we see that we can increase the quality while maintaining the delay. And then now this is what we desire. So it turned out that this kind of learning to decode is beneficial, both in terms of the actual decoding objective and in terms of designing an algorithm. Because designing a new algorithm from scratch manually is often impossible. So the interesting thing, so I'm about to actually wrap up my talk, is that I started working on neural machine translation. Actually, back then it wasn't even called neural machine translation. That was not even a term. Just using the neural net for machine translation in 2013 when I was in Montreal under the supervision of the Yoshua as a postdoc fellow. And in 2013 and 14, Yoshua actually suggested a number of things. He talked about like building just one neural net for end-to-end translation. And then, like I followed, that became neural machine translation system. He talked about, like the awesomeness of the continuous vector space, which allows us to share multiple languages. And then that became multi-way, multilingual, nowadays even multimodal neural machine translation systems. And then he talked about all those pre-processing routines, or like the tokenization, segmentation, and so on are too complicated and then probably unnecessary, and then they have to be trained together in order to maximize the translation quality. So he suggested using the simplest form of surface or the sentence possible, and then that became the character level neural machine translation. He's been a very, let's say, big advocate of the hierarchical recurrent neural net already from 90s. So he had a couple of papers in 1994 and so on. And then that has also become a hybrid character word level neural machine translation system. And then unsupervised learning is a thing that always fascinates Yoshua, and then that has just been realized a bit in terms of the unsupervised machine translation system. And then last year he wrote a technical report called titled Consciousness Prior, and then one of the realizations, possible realizations from that technical report is the trainable decoding. So that is, you're going to train a recurrent neural net to make a succinct abstraction of the real world, and then only on top of that, you're going to do a lot of different things, how to use that abstraction. And then that idea is actually present in the trainable decoding. And then a few other things that Yoshua suggested back then was to use the denoising autoencoder instead of doing the autoregressive modeling. So, and then already Jiatao Gu, who was doing internship at Salesforce last year, was able to make a non-autoregressive modeling. And then we decided to dig into a bit further and then try to use an idea of the denoising autoencoding to get a better numbers. It's the ongoing work. But this one as well, Yoshua told me to try in 2014. And then back then I just told him that, but Yoshua, recurrent neural net is doing already amazingly well. Why do we want to do the denoising autoencoding? I was wrong, right? So Yoshua was correct back then. And then it turned out that it does really help quite a bit, but like we'll see how it goes further. Yep, sorry. So this is it. And then I asked Yoshua, so Yoshua, now what you told me, what you suggested 3 to 4 years ago, have all been correct. You're right, I should have listened more carefully. So what should we do next? And then what Yoshua told me was the grounding. And then grounding as in now when we try to learn or to train a neural net to understand language, the neural net needs to know how the language is grounded in the real world, either by observing other modalities or via interaction with other agents or humans. And that is the one thing that I'm trying to work on these days. And then we'll see in 3 years whether Yoshua was again correct. Well, that's about it. Thanks for listening. If you have any questions, just feel free to ask me.
Thank you very much for the talk. Does anyone want to ask any questions? If you want to ask a question, please come here so that Kyunghyun can see you.
Hey, thanks for the presentation. So about the first part of the presentation, when you presented the translation model with the information retrieval part, but the intuition you gave felt like more intuition to use that model on tasks like question answering or natural language inference. Did you try that model on that task, or are you familiar with any tries?
So there was another paper from the group in IBM that was published almost at the same time that uses this idea for the text classification. So what they did was, okay, given a text, they need to do the classification, let's say classification into different categories. What they did was to retrieve training examples and then look at how the similar examples, which category similar examples belong to, and then use it. So that's the one paper that I'm aware of. And then starting from our paper, I believe there are a number of groups working on trying to extend this idea into natural language inference using the external data, as well as doing the question answering. So one paper that was unfortunately rejected from iClear, but this submission that is available online at the moment, natural language inference using external knowledge. So that paper kind of hints at how that kind of external knowledge can be used to do the natural language inference better. Except that the execution was kind of, let's say, very simplistic, so I'm not sure whether the result is conclusive enough, but that will be the one paper that you want to look at. And also, in terms of the machine reading and question answering, I believe Russ is going to talk about it right after my talk, so yes. You can ask him, yes.
Okay, thanks, I will.
Any other questions? Okay. Do you want to come here? There is the camera.
Hello, Andre.
Hey, how's it going?
Good, good.
So this is Andre Martins from Babel. So I have one question about this line of research on unsupervised machine translation. There's always this thing that has been puzzling me, which is, you know, when you have this approach to take your monolingual embeddings, you know, and rotate them so that they can be more or less superimposed. It just feels like, you know, there's already, you know, the whole idea relies on the fact that there is a very similar manifold structure in the manifold embeddings, because with just a rotation, you don't have a lot of degrees of freedom to superimpose the words. And if I recall correctly, in these earliest works, I don't know if it's the same in the unsupervised MT papers, you learn these monolingual embeddings on Wikipedia or something, which is not exactly, you know, it's not parallel data, but it's also, let's say there's some kind of weak supervision there because the data is a little bit parallel. Do you think if you know, try this approach in corpora that is not parallel at all, this would not work? Do you have any comments about that?
Yeah, so yeah, that's actually an amazingly good point, and then point that I don't want to emphasize is that so I do not think with a finite or the small amount of data they are not aligned. I don't think it's going to work. So somehow I think ideally, if we can use all the text available in the word, we would believe that the manifold induced by that infinite amount of data will look similar across the languages, because, you know, like it's all anyway grounded in the actual world where we live in. But when we have the finite small amount of data, and then if we try to induce a manifold from that, if there is a huge shift in the domain, the induced manifold will look very, very different, and then they probably cannot be aligned. So yeah, I think it's important to have the kind of, let's say, comparable corpora to start with. Yes, but that's also up to kind of experimentation, and then of course, what does it even mean to have comparable corpora is a big question. Yes, good point. Yes.
Thank you.
Hi, Kyunghyun.
Hi.
As you know, our lab is doing dialogue systems research, and of course you know that a lot of models which we now use for dialogues, they came from machine translation. So what do you think, how machine translation is different from the dialogue? And what is missing in the current machine translation models, sequence-to-sequence models, what we need in dialogue? So where we should look, like, can you play a role of Yoshua for us in dialogue domain?
Well, I mean, like trying to be like Yoshua is always my goal, except that it's very, very difficult. But yes, yeah, indeed, translation and dialogue modeling are indeed similar. And then what I believe is that essentially, I think the major difference, first of all, comes from the fact that how much, let's say, extra context you need in order to do a good modeling. In the case of translation, already even a single sentence contains most of the information that you need. Not all, clearly not all, but a lot of information you need in order to do the good enough translation. On the other hand, in the case of dialogue, just looking at a single utterance, or even a history of, let's say, tens of utterances in a single session is definitely not enough as a full context to predict the next utterance. What it means is that it's all about how efficiently and then how effectively you can incorporate extra context. And then in the case of translation, one way is to, okay, a lot of people are trying to go into the direction of, okay, let's try to take into document level context. And then also, if you want to go further, maybe some social context. So in the case of translating between, let's say, German and English, or like English to Korean, you want to know about the social context in order to get the politeness level correct, for instance. On the other hand, in the dialogue, you need even more, right? So you want to know about the social context as well as the, let's say, temporal context. So for instance, if they are friends, so that's going to be a social context, and then the time is, let's say, around the dinner time, and then they've been talking about something to eat, maybe among possible utterances next time, that actually narrows down into the, let's say, utterances that have something to do with eating or the restaurant or the going out. So that kind of, let's say, how to incorporate the context is going to be a big thing, and then probably that's where the dialogue modeling needs to do much more on the compared to the machine translation. So how do we incorporate the context? I don't know. I want to know. Yes, definitely. But I think there is some interesting direction in the intersection between this non-parametric neural machine translation system and then the dialogue modeling with a larger context, in a sense that you can collect all those contexts, but it's difficult to tell which context is going to be relevant. Maybe for that, we can use this kind of retrieval algorithm to quickly and then very accurately retrieve the very few, let's say, attributes that describe the current context as succinctly as possible, and then incorporate that into the dialogue system. So that could be one direction, perhaps, if I to play Yoshua Benchio at the moment.
Yeah, great. And what do you think, just in general, we have told before, just a couple of minutes ago, that then your learn machine translation task, you create something like a universal manifold of which is grounded in the real world. And this can provide you with like a model of the world which can be used for the dialogue. So it's like a common sense knowledge which you can use for the dialogue. What do you think? How is it possible to use this kind? So it's not the only language model. Now we are talking that we can use language model to improve like named entity recognition task or something like this. But this is not language model. It's like a world model. So what do you think? Is it possible to use this like world model induced from language for the dialogue? Or
right. So one thing that I believe, and then I think a lot of other people have started to believe in, is that how we are doing the natural language processing or the language learning using the deep neural net completely lacks the interaction component. So at the end of the day, like the reason why we have language and why we use the language, large part of that is to interact with others in a social context. And then now that part is currently not being used extensively in order to train these language understanding machines, or hopefully one day they're going to be language understanding machines. And then now the idea is that, okay, what are the things that these machines can capture more if they were allowed to interact with other agents or interact with the world? And then people have, so the difficulty there is that it's really difficult to design an experiment where you can have the actual interaction and then use it to train a model. So people have started to bring in the simulated environments. So there were like 3 different simulated environments proposed simultaneously by like Facebook, Montreal, and maybe Google DeepMind. And then what I believe is going to get us is that essentially it's all about predicting the future. If I can predict the future better, then I can narrow down what I should do or what I should say. And then these interactions is giving the model a better idea of, given the constraint given by the word, what are the more plausible future that is, and then based on that we can choose better. So in some sense, I'm not really answering your question because I don't know the answer to, but this kind of, let's say, incorporating the interaction might change quite a lot, and then that will be the next step before going into modeling the full word. Yeah.
Okay, thank you a lot, and thank you for agreeing to give a lecture for us. You are like a veteran of our hackathon, so that's your second lecture.
Yes.
Thank you a lot.
Well, thanks for the invitation.